All right, so last time we just started this class by talking about some notations used in asymptotics. And I would say the most important two relations are the small o and the big O. So between those two, I would say we will see the big O more often. And these two notations apply to a sequence of numbers, fixed numbers. So there's no randomness involved. Okay. So what we talk about is that between two sequences, we can use small o and big O to describe their relationship. And so you can see this is the more general case. And for a special case, you can replace this sequence by a constant, say C, but still that same definition applies. So when we write AN as small o BN, this is based on limit. Okay, so in other words, it says that AN is slower than BN when n is large, or if both of them going down to 0, then AN goes down to 0 faster than BN does. So mathematically, we write that AN over BN, this converges to 0 as n goes to infinity. So this is the definition of the small o. And so you can see that roughly speaking, we can think of Bn as an upper bound on An, and it's a very, I would say the upper bound is very big, such that we will have this ratio going down to 0. While the big O is also a sort of upper bound, but it's more general than small. So small o belongs to big O, but big O also includes the same order relation. So when we write AM as big OBN, we mean that AN grows slower, more slowly, or as fast as BN, subject to a constant. So we include that same order in big O. So in other words, for the rigorous definition, it means that there exists two things. One is a bound, upper bound, and an index, n0, such that we would have this absolute ratio under m for all n greater than n0. It means that after a certain index or certain position, for all the remaining AN and BN, their corresponding ratios, absolute values are bounded from n, from the above. So m is an upper bound. So you can see that this small o definitely satisfies this. It's an even stronger condition. It must go down to 0. And this only requires it to be bounded. So for this one, right, if you recall, if we write down the definition in terms of limit, mathematically, what do we write? We can actually say for any positive epsilon, there exists an index on order n0 that depends on epsilon, such that we would have the absolute value of AN over BN. We will have the absolute value of AN and BN less than epsilon for all n greater than this n0 epsilon. Okay, so you see, if you compare these two things, there's a difference. So first of all, here, epsilon is any small neighborhood size. And given the epsilon, there exists a corresponding n0 that depends on epsilon. So you can imagine, usually when epsilon is smaller, this n0 epsilon must be bigger. We must go deeper later into the sequence. And then we satisfy that this ratio is under this epsilon for all the later n. While here, we have the upper bound and n0 that exist but there's no, but basically there may be no relation. For example, if there's an upper bound n, right, that applies to all the n, then n0 could be 0. So we could have this n0 that go from 0 to 1 or 2, and these all hold. And also this m may not go further down. For example, this m may be 10, but you cannot let it go down to 5, then this upper bound doesn't hold. So these are the differences we must realize. So this is called just small o, and this is big O, and big O is more often used. So last time we also gave you the probabilistic notation, the small o in probability, big O in probability. Let's talk about that further. So small o p, this means improbability. And big OP, also improbability. So when we say improbability, we need to add another layer. So basically for the statement here and here, they do not hold for sure. They hold with high probability. That's the thing we need to consider. So in other words, when we let me put it here. When we talk about random sequences, xn and yn, we need to realize that they are random, so nothing holds for sure. So when we say with high probability, so you will often see this in a lot of papers. Usually short as WHP. What does it mean? So it means that we need to have a small probability for violation. So usually we say this delta is between 0 and 1, is small, and we call this violation probability. Okay, so if you can say something like for any for any delta, the violation greater than 0, for any positive violation probability, we exist some event, or I should say, maybe this is too vague. I'll make it more general here, sorry. So for any epsilon greater than 0, so if we have the probability of some event, which may depend on delta, holds with probability at least 1 minus delta. Then we say this event holds with high probability. So for any violation, you could find the corresponding event, and this event holds. So in this case, this delta, if you think about it maybe as 5%, then we're saying this event happens with probability at least 95%. So this event doesn't happen for sure for 100% probability, but still it happens often enough. So we can be sure that this is some event we can trust. So this is just a very brief statement, but coming back here, right, small op, then what we want is that this limit, this convergence holds with high probability. Then what do we say? So basically, using this notation, we're going to say that given any delta violation for probability greater than 0, and also any epsilon greater than 0, something we need for the limit, there exists another n0 that depends on both the delta and the epsilon, such that the probability that this event an over bn less than epsilon will hold with probability 1 minus delta for all n greater than this n0, delta epsilon. So you see now the argument gets more complicated because of this additional layer about probability. Previously, delta is just 0. So this event holds with probability 1. So we don't need to say that. Then, oh, sorry, my bad. This is xn, yn, right? So now, because this ratio becomes random, so we can never say this ratio is less than epsilon for sure. But we want this to hold with high enough probability, at least 1 minus delta. Does this make sense to everyone? Okay, yeah, this is a small OP. Then for big OP, you can think about it maybe for 1 minute, how to modify this big O into big OP. The hint is that we need this event to hold with high probability. Okay, I'll start writing, and then you can tell me whether it's something that you also think. All right, so still given this violation probability, there exists n delta This is it. So still, the argument becomes that given a violation tolerance, right, a tolerance on the violation probability, we can find an upper bound on the ratio and also an order in the sequence, so that the ratio absolute value is under that upper bound for all the n after this order with probability 1 minus delta. So I think this is something I want to suggest everyone. So if you are not familiar with the small O, big O for fixed sequence, if you directly jump into here, for example, you can check these two definitions on Wikipedia if you Google for big O in probability. It may be a little overwhelming because you have so many layers. But if you start from here, once this makes sense to you, and then you move on to high probability, it should be easier. So high probability is just another layer added to the event. All right, so any questions? And so this big OP is so often used in statistics literature, especially when we talk about the performance of an algorithm for estimating a parameter. We want to say the estimator is doing very well. One way to say that is the mean squared error for that estimator will go down to 0 in probability as n goes to infinity, right? So in that case, what we want to say is this. So basically, if you can say, okay, the squared error, say theta n hat minus theta, the true parameter value square, if you can say this is, let me see, small o1, small op1, then you are telling yourself that this thing is going to 0 in probability. This is what it means. And we are going to talk about convergence in probability today. But I think this already gave you a flavor about what it means. So it means that something happens with high probability. But if this is not specific enough, right? Small POP1 only tells you it goes down to 0 in probability, but doesn't tell you the rate. If you write it as big OP1 over M, then this is more specific. It not only tells you that it goes down to 0 in probability, but it tells you the rate for its convergence to 0 in probability is at least 1 over n, or even faster than 1 over n. So this is something you may see in the paper. It gives you the rate. Furthermore, I think if you may see in some paper that people use big omega. That's something I want to say as a side note. So the notation is this, or its probability version. Omega p. So these two things are on the other side of big O and big OP. So they are talking about not the upper bound, but the lower bound. So basically, if I write AN as big omega BN, okay? So in this case, what I actually mean is something similar to that. So exist n lowercase m greater than 0 and n0 such that I would have AN over BN bounded by n, lowercase m from the below, for all n greater than n0. This is the lower bound, omega. And similarly, you should be able to define omega p by yourself. I think the omega notation was often used in computer science in terms of the algorithm complexity. So it's the lower bound complexity, while big O is the upper bound complexity. So in other words, if you think about complexity as something bad, right, or computational time, something bad, then big O gives you the worst case scenario, while omega, big omega gives you the best case scenario. Okay, so I think these are something I want to add to our last lecture. Do you have questions? There's something wrong. Okay, so if there are no more questions, then let's continue our lecture today. Today, we're going to talk about 4 modes of convergence for random sequences. And we're going to go from the easiest, maybe I think the easiest to the more difficult ones. So first of all, I want to, and this is our lecture 2. I'll call 4 modes of convergence. Okay, so the idea is that we still have a random sequence, and we also have a random variable as its limit. So we want to discuss the case for xn converges to x as n goes to infinity in 4 different ways. And I will give you a preview. The first one is we call convergence in D, or convergence in law. So in the notes, we use convergence in law, but you may see convergence in D distribution in some other textbooks. In distribution or in law, they mean the same thing. The second mode is convergence in probability. And this is the one we're going to talk the most in probability. Also the first one. And in the later class, I think we'll mostly focus on these 2. They will happen the most in our large sample theory results. And other 2 that are used less often, including the convergence in the Rth mean. And most often we have R equals to 2, so convergence in quadratic mean. This is useful when we talk about square loss, how it changes as our sample size goes up. And the fourth one is I think mostly used in probability, but in statistics, we usually may not be able to achieve that. Okay, this is almost surely. And also I should say it has a different name. So almost surely or with probability 1. They mean the same thing. Okay, so we will talk about those 4 modes of convergence today. So I want to do a survey first. How many of you here have learned this before? Or at least have, okay, so 1 person, 2, 3, 4, 5, 6, and okay, 7, maybe less than 1/2, but still quite a number. So maybe any volunteer from you guys to just briefly say what you still remember about those things. Yeah.
I think I remember that like almost sure.
Yeah, that's good. Yeah, exactly. That's something you should know after learning this. So may I ask, did you learn this from a graduate level class or undergrad class? Undergrad, from a probability class, right? Okay, yeah, that's good. So any other volunteers to say more? But did you feel like these things are a little difficult to understand when you learned it before?
Yeah, I just like intuitively like actually
understand. Yeah, I totally agree. I think that's something I felt when I learned it as a student. I think I first learned it in the abstraction. So I memorized the concept, the definition, and I know, okay, how to use the definition to solve problems. But basically that's it. But I think I gained more and more intuitive understanding or intuitions behind these things as I started teaching them. So I'll try to give you an example. So I think it will make it easier for you to understand. So as I said in my last class, right, to really concretize random variables, you need to think about its realizations. So I think that's the best way to think about it. So let me write it on this hand side, on the right-hand side. So let's say the random sequence is also x1 to xn, right? And we have some limit x. They are all random. So this is the sequence. This is the limit. And so we are wondering about the relationship here. Okay. So if you think about realizations, then we get numbers. So I'm just going to use lowercase to represent the realizations, and you should think of each lowercase as a number in your mind. So I say we have m realizations in total. In other words, for each random variable, I do sampling for m times. So this one becomes x11 to x1n. This becomes xn1 to xnm. Okay. And for the limit, it also has its own realizations, x1 to xm. So if you think about it this way, then every realization give me a sequence, a number sequence, a sequence of numbers, and the limit as a number. So then you can see there are multiple ways I can talk about their relations. So for example, what would be the ideal case? In the ideal case, I would have each sequence of numbers converge to this limit number. right? So if I do have this, so case, maybe I should say it, if I have this x and I'll call it x and I converge to the limit xi as n goes to infinity for all I from 1 to n. For each realization, I have the number sequence converge. Then in this perfect case, what do we say? Actually, this is what we call almost sure convergence. Okay, so I think this is a very easy way to understand it before we talk about the mathematical definition. So in other words, every realization has a convergence. We can see why we say this is very strong. And I'm trying to simplify things a little bit by ignoring the fact that we should say this holds with probability 1. But since we are having realizations, if something happens with probability 0, we shouldn't be able to realize it. So that's why I think it's fine to say that intuitively. So this is one case. But often we don't have this, right? So I'll say, let's call this A. Then if A does not hold, does not happen, what else? What other possibilities may we have? So another possibility is that if we think about the other 3 modes, what do they mean? So here I'm trying to get for each realization, I'm interested in getting the difference between the nth one and the limit. So let's say that I calculate a difference. I'm going to call that, okay, absolute value xn1 minus x1. Okay, I get a difference here. And I go down for the nth realization, I can get xnm minus xm. So even if I don't have this convergence in every sequence, but given those differences, I can say 2 things. The first is that, so basically, I want to look across all the m realizations and say 2 things. So the first way is to check whether each difference is big or small enough. Okay, so check if this xn1 minus x1 is less than epsilon, a preset epsilon or not. And I do that for all the m differences. Okay, I check each one. So you see, once I check it, I will get a binary, 0 or 1. 1 means it holds, 0 means it doesn't hold. And then out of the m binary results, I calculate the proportion of ones. Okay, so for those, I get a proportion of ones. Then something interesting would happen. So if I observe this proportion, which of course depends on the n, right? I call that Pn. Okay, I call this Pn. If I observe that the Pn goes up to 1 as n goes to infinity. In other words, as my n moves to the large side, to the right side, the proportion of realizations such that this small neighborhood constraint holds is going up to 1, going up to probability 1. Then we say this is convergence in probability. That's what we mean. So in other words, convergence probability is never concerning the convergence of one realization, but it looks the average across all the realizations. And it's possible that we satisfy this convergence in probability because on average, the difference between this n, xn, and x, the limit, is getting smaller and smaller. But it's possible that I have some swapping across the realization. Sometimes in one realization, the number gets bigger. So that's why you don't have convergence in every realization, but you may still have this convergence in probability. So once you understand this, then you can easily construct a counterexample where you have convergence in probability, but not convergence almost surely, which we will do later. But I want to give you some intuitive understanding first. Does this make sense to you, to everyone? Okay, that's the second. So we talk about almost surely in probability. Then if this is not the case, we check another case. So basically now here we binarize, right, this difference by setting epsilon as the threshold. We can also do this. We calculate the average. Let me give this another notation. I call this En. I define this as the average of the n realizations, right, from 1 to m, and the difference x ni minus xi absolute value, and I raise it to a power r. So, okay, I should say here, the r must be positive. I forgot to say that, with the r positive. So this is the rth power difference, right? Average across the realizations. If we have this En goes down to 0 as n goes to infinity, then we say this is the convergence in the rth mean. So you can see it's similar to the convergence in probability because both look at some sort of average across the n realizations. The difference is that in the definition of probability, convergence in probability, we binarize the difference into 0 or 1 by thresholding at epsilon. And epsilon is the preset neighborhood size. While here, we don't binarize the difference. We raise it to the power r, and we take the average. So therefore, you can see that if in your sequence, you have some outlier realizations for which this difference is especially big, then in that case, this En may blow up, but the Pn over there or that proportion will not be affected because no matter how large it is, when it's exceeding epsilon, you still get a 0, right? So understanding this can give you a way to construct a counterexample where you have convergence in probability, but not convergence in rth mean. Yeah. Okay, so that's the third case. Finally, convergence in distribution. So you see, in the above 3, right? So almost surely probability, rth mean. In these definitions or in these explanations, we have looked at the coupling of the realization in the sequence and the corresponding realization in the limit, right? We look at their relations. So therefore, you can imagine that the dependency between the sequence and the limit would definitely play a role because we look at them in pair. But for the last definition, let me see. So if A, B, C don't hold. Okay, so if we don't have the above 3 convergence, we may still have another type of convergence that doesn't require the coupling here. So for the last one, we just look at the distribution for each x1 to xn. So in other words, what we look at is here. So from here, I'm going to get a distribution. I call this F1 CDF, okay? The distribution across the M realizations. And I also have Fn here. And for the limit, I have an F. So if I can say that the CDF function, if the function CDF converge to the CDF of the limit in some way, okay, I'm going to be more specific later. But if you do have the convergence of the CDF function, then you will say the xn converges to x in law or in distribution. So you see, when I talk about this, then the dependency between xn and x does not get into play because I'm looking at each random variable's distribution separately. So in other words, graphically speaking, if you think about the CDF, maybe I'll talk about it later, but you can think about this as just a distribution, another distribution. So if the distribution is getting closer and closer to the distribution of the limit, then you're good. And there could be dependency between the two, or there could be not. So just to make an extreme example, let's say that I have x as uniform 0 to 1, okay? And xm, I define it to be 1 minus x. Then if this is 0.1, it's 0.9, 0.2, 0.8. If I define that way, then I can see there will be no convergence in each realization at all, right? Because they're not getting closer. However, look at its distribution. This 1 minus x is still uniform 0 to 1. So they share the same distribution. So you have convergence in distribution. Okay, does it make sense? Okay, and then when we say central limit theorem, it is convergence in distribution. Because when we say that sample mean after some centering scaling is convergent to uniform 0 to 1, oh sorry, Gaussian normal 0 to 1, then we are thinking the limit random variable is a Gaussian 0, 1, Gaussian 0, 1 random variable, right? But that random variable can be any Gaussian, right? And that Gaussian random variable can be independent of my sample mean. That's totally fine. But that's just convergence in distribution. Okay, so this is the intuitive definition of the 4 modes of convergence. And we haven't really started the mathematical definition yet. But I think this impression will be very helpful. So it can help you understand the mathematical formula later. And also, I want to say that we are giving you the general form, but in practice, the cases you will see would actually be simpler. So in most cases, when we talk about convergence in probability, the limit is usually 0. Okay, so that's a constant limit, make things simpler. And now also here, convergence in RFB, the limit is often 0. Yeah, it's often 0 as well. That also makes it simpler. So you have 0 here. And also for the convergence in CDF, in distribution, sorry, usually this CDF is something of a very well-defined distribution, like Gaussian, chi-square, right, in practice. Okay. So, and what's more, why do we care about the convergence in distribution or law? The reason, as we will see later in the lecture, is that this limiting distribution, CDF, as I said, is usually well-defined with a closed form, and we can easily use it to describe our statistic, right? So because our statistic, if we don't do the asymptotics, it may have a very complicated distribution to mathematically analyze. But with a closed form, then we can easily calculate its tail probability, right? The most important one is the p-value, right? If you do a statistical test, so that will be applicable. So again, this is for simplification purpose. Okay, so any questions before we continue? Yes. Right, exactly. Yeah, so actually here we didn't do thresholding by epsilon. Right, so I should make it, but you will see this clearer as we move on to the mathematical definition. So specifically, this says that for any epsilon greater than 0, right, we should have this thing, or maybe I should make it better. Yeah, I think that's a very good idea. I should put epsilon here, so it makes more sense. So for any epsilon neighborhood size, we can define this we can do the thresholding, and we can calculate the proportion of ones, and we will always want this proportion goes up to 1 as n go to infinity for any epsilon. Right, so that's the convergence in probability. So in other words, we only care about the realizations when xn falls in the epsilon neighborhood of x. But for the ones outside the neighborhood, we don't care how large the difference is. Right? So in other words, outliers do not really affect here, but they do affect here. Right? So in this case, anything is averaged by their value, by the difference raised to power r. And you can see why this makes sense when we talk about the MSE of an estimator, because you want the estimator to be close to the true parameter value in every case. And you don't want to have an outlier where the estimator value is too different, too far away from the true value, even though that outlier case happens very rarely. So in probability, as long as it's rare, it's okay. But in this way, it matters. So that's why I would say these things are human formulations for evaluating things, right? So there are these are some criteria, and they examine different aspects. Yeah. And that's a very good question. Any other questions? All right. So now I'm going to erase this part. I'll keep that realization diagram there for your reference, and we'll give you the formal definition now. Okay, so we'll go one by one. So the first definition is for the convergence in law. So xn convergent in law to x is defined as the CDF of xn. So I'll write it here. So that here I use that. Maybe I'll change it to be consistent. fx1, fxn, and fx. Okay. So if fxn, the CDF evaluated at any value in the domain x is converging to the CDF of x, the limit, evaluated at the same x as n goes to infinity for all x where f is continuous. Okay, so what I mean is that we care about all the values in the domain, or all the points in the domain where the limiting CDF is continuous at. So we call this a continuity point. So this is a definition about functions. And for each value, each point that's a continuity point, we need to have this point-wise convergence of the sequence of CDFs to the limiting CDF as n goes to infinity. Okay, so for different x, the convergence may happen at a different rate, right? So in other words, mathematically speaking, what we want to say is, so given, or I should say, for any, or I should just say, any continuity point x, okay, we start from here, given an x and any epsilon positive, there exists another or index n0 that depends on x and also the epsilon, such that we would have fxn x minus fx x less than epsilon for all n greater than n0 x epsilon. Okay, the reason I write this out is to remind you that the n0 depends on x and also epsilon, right? So as you change to a different x, then this order may move later or earlier. So this is point-wise convergence. But you know, if you have taken a, I would say, analysis class before, you may have learned there's a uniform convergence of functions. So in that case, this n0 will not depend on x. It's the same n0 for all x. The same n0 epsilon for all x. Okay, so that's it. So essentially, to prove convergence in law, you just need to prove point-wise convergence of functions. That's it. And I can give you an example to help you understand this definition. And again, I think that diagram for realization will really help you. So let's say that I have xn equals to 1 over n with probability 1. So in our case, in our class, when we say with probability 1, you can basically think about this as a constant. In other words, xn is a constant at 1 over n. And x is 0 with probability 1. Okay, so when I have a random variable like this and a random variable like this, right? This is a very degenerate random variable because all the probability mass is at a constant. So in this case, can you tell me whether you think xn converges to x in law? We can think about it in two ways. First, intuitively, if you think about distribution. So here for each xn, its distribution is just a point mass at the value, right? So it starts from 1, then 1/2, 1/3, right, and then 1/n. So you can see that point mass is moving closer and closer to the point mass at 0. So intuitively, we're good. But we also realize that if you have taken analysis before, this 1 over n is approaching n but never reaches n. So that's something we need to worry about. That's the intuition. Mathematically, let's think about what's the CDF. This depends on what we talked about last time, right? How do you write a CDF for this discrete distribution? Okay, so think about it. Okay, f x x n x between 0 and 1. So we can see that if 1 over n is right here, then the CDF will look like it stays at 0 and it's the circle here. It doesn't take the value, but once it hits 1 over n, it will jump to 1, right? And stay as 1. That's the CDF. And so we can see that for every xn, its CDF will look like this, but this jump will move leftwards as n goes to infinity. And for the limit, its CDF will be okay. For the limit, its CDF will start, I should have it, negative side, right? It will stay at 0 on the negative side, circle here, jump to 1, and then stay as 1. So then you can see graphically, we can also see the convergence. And so mathematically, if we do the formula, use the formula, we can see it's also the case. For any positive x, small x, for any positive small x, you can see that by the definition of CDF, after certain n, that CDF will always jump to 1, right? And it will be 1 for the limit. So you do have convergence. The only troublesome issue, so the only issues with the 0. When x equals to 0, as we said, 1 over n will never reach 0. So on the left-hand side, fxn0 will always be 0. But here, fx0 will be 1. So you don't have convergence for that. So let me write this down. So for any positive x, we can have fxn x, it will converge to 1. We said that. And this is equal to the limit. But for 0, okay, this will always be equal to 0. And it's not equal to fx0 because this is 1. So we don't have convergence for x equal to 0. But now the definition comes in. X equal to 0 is not a continuity point. It is where the limit CDF is discontinuous. So we don't care it. Okay, so, but x equal to 0 is not a continuity point of fx. So we don't care about it. And for positive x, we are fine. For negative x, we're also fine because we can show this is 0, this is 0. So we're fine. So the conclusion is that, yes, in this example, we do have convergence in law. So I think this example is very good to show why we need the special treatment for continuity point. All right, any questions? Okay, so I think the mathematical definition for convergence in law is probably the easiest one. So we start from here. Now let's continue. I will talk about the definition for convergence in probability. So just for everybody's information, to make our notation self-consistent, I'll make a note here. So when I say epsilon, I want to call it the neighborhood size. Neighborhood size. So in other words, it's something we say xn minus x less than epsilon, right? We use this to call the neighborhood size. And when I say delta, I want to use this for the violation probability when we have the high probability discussion. So we are more consistent in our notation use. Okay, so now let's move on to the second definition, convergence in probability. Okay. So what do we have? second, convergence in probability. The formal definition says that we have convergence in probability if for any epsilon greater than 0, then the probability that xn minus x greater than epsilon is convergent to 0 as n goes to infinity. So if you remember what we said in the intuition over there, this is exactly what we talk about. We look at the probability for which the realizations do not fall in the neighborhood, epsilon neighborhood, right? That's the proportion we have there. But here we just make it more rigorous as the probability. And we want this probability to go down to 0. Equivalently, right, we can say it's probability that xn minus x less or equal than epsilon, this goes to 1. Right, I think over there, I may write this, I may have written this as less than, not the equal sign, but I think that's a minor thing, right? Whether we take them, because usually when we talk about continuous random variables, the equal sign always have 0 probability. Okay, so this is it. But you see, when we have this convergence to 0 and convergence to 1 in probability, we actually simplify the limit by not talking about the violation probability. When we get a violation probability into play, we are basically writing down the definition of limit. Okay, so the convergence. If we do that, then what is it? What is it? So it's actually this. I'm going to write it down just to be consistent with the beginning of my lecture today. And I hope this can give everybody a deeper understanding. So equivalently, I can write, given a violation probability and any neighborhood size epsilon, there exists an order in the sequence n0 that depends on both delta and the epsilon, such that I would have the probability that xn minus x, this is xn minus less or equal than epsilon. This happens with probability at least 1 minus delta for all n greater than this n0 delta epsilon. So I want everybody to take a look at this. So that means that given the violation probability, a small number, given the neighborhood size, another small number, I can always find a position in my sequence so that all my random variables after this position will satisfy that they are in the neighborhood, epsilon neighborhood of my limit with probability at least 1 minus delta. And because I have this, right, then I can decrease my delta down to 0. That's equivalent to increasing the probability up to 1. Right. So this is the more rigorous way of writing it because it basically writes out the definition of a limit. But before, we just have the limit simplified as this, and we only talk about the neighborhood size. But I want to say this out so you can connect this to that OP notation better. Okay, so any questions? Yeah, I want to spend more time on this definition because I think that's the key. Once you understand the 4 modes of definition, 4 modes of convergence, then the relations between them will become more apparent when we talk about them later. Okay, convergence and probability. Hopefully, I think with this, we will find some of the seminar talks easier to understand, especially when we talk about convergence in probability or big OP or omega P. Okay, so that's the second one. The third one, convergence in the arithmetic. I think that's actually easier to talk about mathematically, even though when we use it, it's not as simple as the definition itself. I'm going to use the wipe to make the board look better for the Zoom. Okay. The third one, convergence in the arithmetic. So here we write xn, x, okay, and for positive r, this is equivalent to, say, the expectation of the absolute difference raised to the power r converges to 0 as n goes to infinity. So if you think about it, this expectation is just a rigorous way of our average, the one we talked before using the realizations, the average of the m realizations. And also something to remember is something I said last time is also, when we talk about expectation, you should always keep in mind or think what distribution is the expectation taken over. And this is taken over the joint distribution of xn and x. Okay, so that's why the dependency between xn and x matters. And also, I forgot to say that in the previous definition for convergence and probability, when we write that probability xn minus x absolute value greater than epsilon, that probability is also with respect to the joint distribution of xn and x. Both are random variables. Okay, questions for this definition? And also we know that there's an interesting relationship between probability and expectation, right? So just a side note, when we say this probability, we can write it in an equivalent way as the expectation of the indicator function. Sometimes we write 1, sometimes we use I indicator that xn minus x is greater than epsilon. These two things are equivalent. And so that's why this is useful when you do some derivations. And so the reason I write it this way is just to come back to your question before. So you see here, this indicator is basically doing a truncation, binarization. Right? Well, here we just keep the absolute difference and raise it to power r. But still, both are some source of average. Okay, the fourth one, which is the definition of convergence almost surely. We give you the intuitive definition as every realization has convergence. So mathematically, we write it as the probability that the sequence xn, n goes to infinity, the limit of xn is equal to x. This event happens with probability 1. So translating this to our intuition, it is the fact that every realization converges to the limit. Okay, so before we stop today, I want to talk about an alternative definition of almost sure convergence, which is very useful for deepening your understanding of the difference between almost sure convergence and convergence in probability. So it's another way of writing this. So it says that alternatively, an alternative definition is that for every epsilon greater than 0, still the neighborhood size, we have the probability that, okay, xk, okay, pay attention to the index k, sk greater than minus x, absolute value less or equal than epsilon for all k greater than n, converges to 1 as n goes to infinity. So this definition is a little complicated because it has 2 layers. The first is that we have a neighborhood size. For this neighborhood size, we have an order n, and we want that there exists some n for which all the sequences, the sequence after this n are all in the absolute neighborhood of x. So we need this for all k greater than n, not just n alone. And this converges to 1 as n goes to infinity. In contrast, if you recall, for the convergence in probability, I'll erase this so you can have a direct comparison. If you recall, we call the second definition, xn converges in probability to x, right? That definition says for any epsilon greater than 0, the probability that xn minus x, maybe I put this equal, then it's better for you to understand. Although it's the same, lesser than equal than epsilon goes to 1 as n goes to infinity. So take your time to compare the 2 definitions. One is convergence in probability, one is convergence in almost surely. So you see, they are very similar. The only difference is the event in the probability. For the right-hand side, the weaker one, we only examine whether xn is in the epsilon neighborhood of x. On the left, we examine all the random variables, including and after n. So not just n itself, but also everything afterwards. This explains the intuition. So you see, for almost sure convergence, we need convergence in every realization. And this convergence is actually implied by this for all k after n. While for convergence in probability, for each position, we look at its average truncated distance to x, right, separately. So we will get a probability here, probability here, probability here. As long as its probability is reducing to 0, we're happy, or going up to 1, we're happy. But here, over there, we care all the subsequence after n. And that's convergence almost surely. So it's a much stronger requirement. So I hope everybody can make sense of this. Essentially, this is implying convergence for every realization. Okay, so I think I will skip the proof that's in the notes, so you can see how we can prove this. It's based on set operations, intersections and unions. And we're going to play with the fact that if the intersection has probability 1, then every set involved in the intersection must have probability 1, something like that. Okay, so we introduced the 4 modes of convergence. Do we have questions so far? These are all the definitions we want to talk about. All right, so 2 more things I want to share with you before we finish today's lecture. So another thing that's weaker or I shouldn't say weaker, but I should say it's different from the Rth mean, is also something we will see in practice. Okay, so it's this. Maybe I will call it as the fifth one, although we don't add it to our four modes of convergence. But it's something I think it's useful. It's this. So does the expectation of my sequence converge to the expectation of my limit? So if you think about this one, it has nothing to do with the coupling of xn and x. We're just getting an expectation here, 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 here. So we get a number sequence, right? We would have, I will say expectation. I have expectation of x1, expectation of xn, expectation of x. So this gives me a sequence of numbers, and the limit is also a number. And I'm curious in whether this helps. So intuitively, right, unless the CDFs are very special, if we have the convergence in law, that is the sequence of functions converge to this function point-wise, we should have this, right? But I'm saying this is just for normal cases. You know, in math, we can always have some special cases to exclude that. So I'm not going to make the claim. But I hope this can help you understand what this says. But interestingly, you know, we can have counterexamples where the strongest mode holds. We have almost sure convergence. So the sequence converges to the limit in every realization, but we don't have this convergence in this expectation. So we can have one counterexamples like this. But you can think about why. The reason could be that in some realization, you are going to have large outliers that will keep your expectation of xn very, very large. Even though you may find that, okay, I'm just making a very special example. Think about that at every position, I'm going to pick one realization to take a very large value. So that will keep my expectation stay large, but the limit will be very small. The reason is that the sequence will always somehow reach a small number and stay a small number. So in that case, we'll have almost sure convergence, but not this expectation convergence. But to avoid the scenario like that, we have two important theoretical results to guarantee. Two theorems to guarantee that there are no such outlier scenarios happening when we have almost sure convergence. We would have the expectation behave well. So I think the key is to make sure that the random variables xn's are bounded somehow, so that you don't have that erratic outlier behavior, and the expectation can be controlled quite well. And you may wonder why we care about this. I think in our statistical application, I mean, to probability, statistics is an application. In our statistics application, we talk about expectation often for bias, right? The parameter estimates bias. We wanted the estimator's expectation should be at the true value. That's something we hope for. If not, if there's a bias, we hope the bias can go down to 0 as n goes to infinity. So that's exactly what we want. Let's say this is theta, the expectation. We hope that expectation of our estimator will converge to the true value. So that's why this is something we often care about. All right, so I think we'll stop here just to leave this as a suspense, very interesting reading, the two theorems to guarantee this, and we will continue next time. So I don't think I'm going to leave a homework today. I think I'll assign the first homework on next Monday. But maybe I can give you a little more time. I'll see. So you can have more time to work on the problems. But the homework will be due on Monday of the 4th week. Okay, so see you next Monday.